Safety saves lives. This simple, undeniable truth is the bedrock upon which our modern world is built, a silent promise embedded in the complex machinery and processes that surround us daily. Beyond the preservation of human life and well-being, safety also saves money, preventing catastrophic financial losses that can cripple companies and economies. Furthermore, robust safety measures help systems work longer and more reliably, ensuring that the services we depend on, public transportation power grids, remain available when we need them most. System safety is not an afterthought or a luxury. It is the fundamental, often invisible shield that protects us from the inherent complexities and potential failures of the technologies we rely on. When we consider the vast web of interconnected devices and processes that define modern life, the importance of a systematic approach to safety becomes profoundly clear. A single, seemingly isolated failure can cascade through a network, creating consequences far beyond its original source. Think of a minor software glitch in an air traffic control system. It has the potential to disrupt travel for thousands, risk mid-air collisions, undermine public trust in aviation. To navigate the world of system safety, we must first agree on a common language. The most fundamental term is the system itself. A system is simply a set of parts that work together to achieve a common purpose. This definition is incredibly broad and powerful. Your car is a system, jiao rao, engine, brakes, steering. A hospital is a system, jiao, doctors, nurses, medical equipment, administrative processes. Even a simple coffee maker is a system, jiao, heating elements, water reservoirs, filters. Because the parts are interconnected and influence each other, we cannot ensure safety by looking at each part in isolation. We must examine the whole system to understand how interactions between components can create or prevent safety problems. With a system defined, we can now ask, what is safety? Safety is the state where a system operates without causing an unacceptable level of harm to people, property, or the environment. It is more than just the absence of accidents. True safety means the system performs its intended functions reliably and predictably, even when faced with minor problems or unexpected inputs. A safe system is resilient. If one small part fails, safety measures prevent escalation into a catastrophic event. Now we introduce two crucial related terms: hazard and risk. Wet floor, loose electrical wire, software bug causing a robot to leave its safe zone. Hazards can be physical, chemical, procedural. Identifying these potential sources of harm is the first critical step. Risk, however, is a more nuanced concept that quantifies the danger posed by a hazard. Risk is the combination of the probability that a hazard will actually cause harm and the severity of that harm if it occurs. You can think of it as an equation: risk equals chance times consequence. For example, a frayed power cord, the hazard, in a busy walkway, has a high chance of causing a shock. The harm, so it represents a high risk. Conversely, a meteorite strike on a building is a hazard with an extremely severe consequence. But its chance of occurring is so low that the overall risk is considered manageable. The goal of system safety is not to eliminate all hazards, an impossible task, but to identify and reduce the highest risks to an acceptable level. Once we understand the basic vocabulary, the next step is to actively search for dangers. Engineers cannot wait for accidents to happen. They must proactively hunt for hazards using structured methods. This process is known as hazard analysis. One of the simplest yet most effective tools is the humble checklist. For a well-understood system, like a standard passenger car, engineers can use a pre-compiled list of known potential issues to check, such as brake system integrity, tire pressure monitors, airbag functionality. Checklists are excellent for ensuring that common, previously identified hazards are not overlooked. They provide a quick, systematic first pass at basic safety compliance. It's a bottom-up approach examining one component at a time. The team asks, how can this part fail? And what is the effect of that failure on the rest of the system? Example, bicycle brake cable. Failure mode, cable snaps. Effect, loss of braking power for one wheel, possible inability to stop. FMEA builds a comprehensive catalog of component failures and consequences. Show FMEA flowchart. The opposite is fault tree analysis, FTA, top-down. Start with a top-level event like car fails to brake. Work backward to find lower-level failures and conditions. Causes are linked with gates, and all must be true, or anyone is sufficient. Example causes: hydraulic fluid leak, master cylinder failure. FTA shows complex combinations that lead to major accidents. For process-heavy systems, engineers run HAZOP studies, hazard and operability. A multidisciplinary team examines system diagrams and uses guide words to probe deviations. No more, less, reverse. Example, pipe, no flow, more pressure. HAZOP exposes hazards from abnormal operating conditions. These tools, from checklists to HAZOP, give engineers the vision to spot dangers before they cause harm. After identifying hazards and analyzing their associated risks, the core work of system safety begins, reducing that risk to an acceptable level. This process is often called mitigation. The most effective form of mitigation is to eliminate the hazard entirely. For example, a cleaning process uses a toxic chemical, a hazard. The best solution is to replace it with a non-toxic alternative. By removing the hazardous substance, the risk of chemical burns or poisoning is completely eliminated. This principle, known as inherent safety design, is the gold standard. When a hazard cannot be eliminated, the next best strategy is to add engineered controls that reduce the risk. This can be done by reducing the likelihood of the hazard causing harm, or by reducing the severity of the harm if it does occur. A classic example is a guardrail on a high platform. The hazard is the height, which cannot be eliminated. The guardrail acts as a physical barrier that drastically reduces the likelihood of a person falling. An airbag in a car is an example of a control that reduces severity. It does not prevent the crash, the harmful event, but it deploys to cushion the occupant, significantly lessening injuries. A powerful technique for improving safety through engineered controls is the use of redundancy. Redundancy means having backup components or systems that can take over if the primary one fails. Commercial airplanes are designed with multiple engines. If one engine fails, the others can continue to power the aircraft, allowing a safe landing. Similarly, critical computer systems often have redundant power supplies and redundant data storage. While redundancy is highly effective, it often adds cost, weight, and complexity to a system. Therefore, engineers must carefully apply it to areas where single-point failure risk is unacceptably high. Finally, if risk can't be sufficiently lowered through design and engineered controls, we rely on administrative controls such as warnings, procedures, training. An alarm that sounds when a temperature gets too high prompts an operator to take corrective action. A clear, well-written emergency procedure guides people on what to do during a crisis. Effective system safety is not a one-time event, but a continuous process that spans the entire existence of a system, known as the safety life cycle. This structured roadmap ensures that safety is considered at every stage, from the initial spark of an idea to the system's final day of service. The very first step in this life cycle is to clearly define the system and its mission. Engineers must have a deep understanding of what the system is supposed to do, who will use it, the environment in which it will operate. Without this clear definition, it is impossible to determine what constitutes safe or unsafe behavior. This foundational stage sets the boundaries and goals for all subsequent safety activities. With the system defined, the life cycle moves into the critical phases of hazard identification and risk analysis. As discussed earlier, this is where engineers use tools like FMEA, FTA. This is not done in a vacuum. It is an iterative process that happens alongside the system's design. As the design evolves, new hazards may be introduced, and existing ones may change. The safety analysis must keep pace, providing constant feedback to the design team. The goal is to find and address major hazards early in the design process when changes are easiest and least expensive to implement. Once the risks are understood, the next step is to decide on and implement controls to mitigate them. This is where the principles of risk reduction are put into practice. The design team, guided by the risk analysis, will choose the most effective combination of inherent safety design, engineered controls, administrative procedures. These safety measures are then formally incorporated into the system's design specifications and built into the hardware-software operational plans. This implementation phase transforms safety from an abstract concept into tangible features, such as physical guards, automated shutdown logic, warning labels, operator training manuals, creating the layers of protection needed. Section 6. The human element. Why people are the heart of safety. No system, no matter how automated, exists in a vacuum. People are an integral part of nearly every system. Humans design, build, operate, maintain them. For decades, accidents were often attributed simply to human error, a convenient label that placed blame on the individual at the sharp end of a failure. However, a modern system safety perspective understands that this is a vast oversimplification. Instead, human error is often a symptom of a deeper problem within the system itself, a mismatch between the system's design and human capabilities. Effective safety engineering, therefore, must deeply consider human factors. This means creating controls that are intuitive and easy to use, especially under pressure, and designing displays and alarms that present information clearly and unambiguously. For example, a control panel that uses color coding consistently, green for normal, yellow for caution, red for danger, reduces cognitive load and enables the correct response. Training. Clear procedures are vital, but must be designed with human capabilities in mind. Simple, direct, accessible, hands-on, realistic. Design must account for fatigue, stress, and workload. A complex, repetitive 12-hour task bakes in high error probability. Good design seeks to minimize stress and make the safe way the easiest way. Ultimately, build systems tolerant of human fallibility. Catch mistakes before disaster. Section 7. Building a fortress. The role of safety culture and standards. Safety culture is the shared set of values, beliefs, behaviors that determine how people approach safety daily. Leaders model priorities, resource safety, participate in reviews, and foster a just culture encouraging reporting without fear. Communication is open and constant. Frontline insights surface risks designers might miss. Standards like ISO 26262 and stringent rules in aviation and nuclear provide common frameworks, rigor, and independent verification. Section 8. From theory to reality, testing. Monitoring. Learning, a safety design is a hypothesis until proven. Testing gathers evidence, pushes limits, and injects faults to verify safe behavior. Power cuts validate failover. Invalid inputs must drive the system into a safe, predictable state. Combine component, integrated, simulated, and physical tests. Document all for certification. In operation, monitor continuously. Mine data for trends and preempt failures. Section 9. Conclusion. Your role in a safer world. In this brief journey, we have seen system safety is a logical and structured discipline dedicated to preventing harm. It begins with a clear language, defining concepts like systems hazards, risks, which allows us to analyze potential dangers methodically. We have explored how engineers use tools like FMEA, FTA to uncover hidden hazards and then apply a hierarchy of controls. Hazard elimination redundancy warnings to mitigate the associated risks. This entire process is guided by a safety life cycle, ensuring that safety is a continuous focus from design through operation. Supported by a strong safety culture, robust standards, and a commitment to learning from real-world feedback and rigorous testing. Safety is not an abstract ideal reserved for engineers designing rockets and power plants. Its principles are scalable and applicable to the world around each of us. The logic of identifying what can go wrong and taking sensible steps to prevent it is a powerful tool for everyday life. Now that you understand the basic concepts, you are better equipped to see the world through a safety-conscious lens. This knowledge empowers you to ask better questions about the products you use, services you rely on, environment in which you work. Safety is a shared responsibility, and an informed public is a safer public. The call to action is simple and immediate. Take a moment today to apply this thinking to one system you interact with regularly. Kitchen stove, bicycle, software application you use at work. Try to identify just one potential hazard that you may not have noticed before. Then, take one small practical step to lower the risk.